So now that we know how to take a derivative, we can look at one of the many applications of a derivative, and that's something called Newton's method. Newton's method. And Newton's method, as you can probably guess from the name, was devised by one of the inventors of calculus, Sir Isaac Newton. And his way has remained as one of the best ways for approximating the roots or the zeros of a function. And it does so using tangent lines. It uses tangent lines to a function. To better visualize that, let's draw us a picture. So let's say we have this graph right here, and we have a function. Newton tells us that in order to find the precise value, or to approximate this precise value of the root of a function, we can pick a point that's relatively close. We can make a guess that's relatively close to the actual root, and we can make that our first guess. And if we draw a tangent line, to the graph at that point, our first guess, our first x, then that will give us a better x, or a better estimate of this root. And that's our x2. And if we were to repeat that process and draw another tangent line, that would get us even closer to the precise root. And each time that we do that, we get more and more accurate. And each time is called an iteration. Now, the only thing we really have to know in order to use Newton's method is the definition of a derivative. And the definition of a derivative, we all know, is f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x and all over delta x. If we were to need to use the definition of a derivative at a specific point, so derivative at a certain point, say c, then we would use f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. And you might look at these for a second and you will say, well, Andrew, are these the same thing? And really they are the same thing, because if we break these down, they are essentially both saying it's the limit as x gets smaller and smaller, or the change in x gets smaller and smaller. The change in x gets smaller and smaller. Then it's the change in y in the numerator over the change in x in the denominator. So these are both the same definition of a derivative. And we can use this definition, this alternate definition of a derivative down here, to approximate a derivative. We can say f prime of c is approximately equal to, if we take away this limit sign, we can say f prime of c is approximately equal to f of x minus f of c over x minus c. And for our purposes, to make it a bit easier to look at, we'll just equate these. But it's good to keep in mind that the average rate of change is actually an approximation of the instantaneous rate of change, or our derivative. And if we multiply both sides by an x minus c, so f prime of c times x minus c, then the x minus c here cancels out and we get f of x minus f of c. And we add the f of c to both sides. It would become f prime of c times x minus c plus f of c is equal to f of x. And this equation we should all recognize, because that's the equation of a tangent line. It's the equation of a tangent line. And because Newton's method uses tangent lines and finds the x-intercepts of those tangent lines in order to approximate the roots of this function, then that's exactly what we'll do. So to solve for any equation's x-intercepts, we know that we have to set the y equal to 0, so we have to set the f of x equal to 0, and we have to solve for x. We have to solve for x. So that's exactly what we'll do. We'll set all of this equal to 0, and we'll solve for x. And before we do that, just to make our lives a bit easier when we get to the actual formula for Newton's method, which we're deriving right now, we'll change the variables a bit, but we won't change the equation. So let's just say we arbitrarily name the x as xn plus 1, and we call this c as xn. Then the equation won't change, so we do 0 equals f prime of c, or xn, times x, which is now xn plus 1, minus c, which is xn, plus f of c, which is f of xn. And from there, we can distribute the f prime of xn into the parentheses. We can distribute that, f prime of xn times xn plus 1 minus f prime of xn multiplied by xn plus, and then the f of xn. And we can move this first part to the other side, or subtract both sides by this, and we will get negative f prime of xn times xn plus 1 is equal to negative f prime of xn plus f of xn. And we're almost done here. Our final step is to divide both sides by negative f prime of xn. And when we do that, we realize that these can cancel out, and we have left xn plus 1, or the x-intercept that we were looking for, on its own side. So now we've solved for the x-intercept. And on the other side, we have these cancel out, which gives us xn, and then minus, because of plus and a minus, so a minus f of xn over f prime of xn. And here we have now derived our formula for Newton's method. To better see how we can exactly use this formula, let's do an example. So we have, say, any function, f of x equals x squared minus 2. And we should all know that that looks something like this. And the precise root we don't know, but we know that the nearest whole number is 1. So let's just say we make our x1, our initial estimate, equal to 1. And this formula tells us that if we have this xn, in this case is our initial estimate x1, then we can find x2, which is a better guess. So x2 is equal to x1 minus f of x1 over f prime of x1. And x2 is basically, if we drew a tangent line to the graph at x1, it would give us x2, which is the tangent line's x-intercept. And that should be a better guess, a better estimate of the precise root. So now we've set x1 is equal to 1, and our formula tells us that we need f of x1, or f of xn. So our f of x1 is equal to f of 1 is equal to 1 squared minus 2 is equal to negative 1. And we need our f prime of x1. Our f prime of x1 is f prime of 1, and since the derivative of this is 2x, it would become 2 times 1, or 2. And when we plug these values in, we have x2 is equal to x1, which is 1, minus f of x1, negative 1 over f prime of x1, which is 2. So we get 1.5. And after only one iteration, we've actually gotten a lot closer to the precise root, which is 1.414. And as you can see, here we have done Newton's method, which is one of the most useful applications of a derivative.